Hello there, and welcome to the Astral Lab, where the night sky is allowed to take its time, the questions arrive slowly, and the universe is studied at the pace of a quiet evening. Tonight we are looking at something that should be simple to define: the largest galaxy we have ever found. One galaxy, one number, one answer. Except, when you actually go looking, you find that the answer keeps changing, not because the galaxies are growing, because every few years somebody quietly looks at old data with new eyes, and the ruler we use to measure the universe extends a little further than the day before. A few decades ago, the answer was a galaxy first catalogued in 1790. A few years ago, it was something 4 times larger. Last year, it changed again. And that one is so long, it stretches across 140 Milky Ways, set end to end. So which one is the largest? And what does largest even mean when a galaxy can be made of stars, or jets, or invisible halos that nobody can see directly? Now then, get comfortable. Let your shoulders drop. We are going to spend some time with this question. For most of human history, when somebody wanted to draw a galaxy, they could fit it on a page. The early astronomers who first turned telescopes toward the smudges in the night sky did not know what they were looking at. They saw faint patches of light, soft and oval, slightly fuzzy at the edges. They called them nebulae, which in Latin simply means clouds. The word was an admission. They knew they did not know what these things were, so they used the most honest word available and waited for the next century to bring better instruments. When better instruments did arrive, the clouds resolved into something stranger. Each one turned out to be an island, a separate collection of stars sitting at distances so large that the numbers had no human comparison. The closest of them, the Andromeda Galaxy, was found to be more than 2 million light-years away. That meant the soft cloud you could see on a clear winter night, just barely, with the naked eye, was actually the most distant object most humans had ever looked at, ever, just by going outside. And it could be drawn on a page. Andromeda fits comfortably into a single photograph. So does our own Milky Way if you make a good simulation of it. So does almost every galaxy in the catalogues. Roundish, spiraled, sometimes a soft oval, sometimes a flat disk, sometimes a tangle of dust and light, but always something with edges. Something you could circle with a pen. For most of the 20th century, this is what a galaxy was understood to be. A bounded object, an island of stars, a thing that ended somewhere. Tonight, that quiet idea will come apart, because the galaxy this video is about, the largest one we have so far found, does not fit on a page. Not the way you fit a circle on a page. Not as a single round thing with edges. It is so long that when astronomers want to show it in a journal article, they cannot put the galaxy and a Milky Way comparison in the same image at the same scale. The Milky Way disappears. It becomes a dot. The dot is so small that the people designing the figure usually have to add a tiny labeled arrow that says, "This is where our entire galaxy would be if it were here." Our entire galaxy, reduced to an arrow. That is not an exaggeration. That is just what the scale demands. There is no clever angle, no choice of zoom, no trick of perspective that lets you fit the largest known galaxy into the same image as our own at a useful size. The math simply does not allow it. The thing is too long. And the strangest part of this whole story is that it has been sitting in the sky the entire time. The light from the galaxy we are about to discuss has been arriving at Earth for billions of years. Every observatory built in the last century has been bathed in that light, every night with the dome open. The data was always there. We just had not yet learned how to look at it correctly. A galaxy that does not fit on the page. It sounds like the kind of thing someone makes up for poetic effect, but is a literal statement about a real object. The pages we use have to be redesigned. The scales we draw have to be redone. The mental picture of what a galaxy even is has to be quietly let go. That is what we are going to do tonight. Let it go. Then build it back, in a new shape. Take a breath if you need to. There is no hurry. We are going to walk into this slowly. Before we look at anything large, it helps to know where we are standing. You are on a small planet on the outer edge of an arm of a galaxy that, by most modern measures, is considered medium-sized. Not small, not particularly large. Comfortable. There are bigger ones nearby and smaller ones too, and the Milky Way sits somewhere in the middle of the local population, doing what most galaxies do, which is to slowly turn around its own center while quietly making new stars at a calm and steady rate. The Milky Way, measured across its stellar disk, is roughly 100,000 light-years wide. Let that number sit for a second before we move on. 100,000 light-years. A light-year is the distance light travels in one full year. Light is the fastest thing in the universe. It moves at nearly 300,000 kilometers per second. At that speed, a beam of light could circle the entire planet Earth more than 7 times in a single second. Now imagine that same beam of light moving at that same speed for one full year without stopping, without slowing, without ever turning back. That is a light year. It is a length, not a time. It is the answer to the question, how far can light go if nothing gets in its way? A light year is roughly 9.5 trillion kilometers, 6 trillion miles. The number is so large that the units stop being useful. Nobody travels in light years, nobody can. The closest star to our Sun is about 4 light years away, and even at speeds that would melt any spacecraft we know how to build, getting there would take a human lifetime or several. That is 1 light year. Maybe 4. The Milky Way is 100,000 of them across. If you began at one edge of our galaxy and moved at the speed of light, you would need 1,000 human lifetimes, stacked end to end, just to reach the other side, and you would not see most of it while you travelled. Light moves quickly compared to anything we know. It does not move quickly compared to a galaxy. There is one more comparison worth holding before we go further, because it can help the number feel less abstract. Imagine, for a moment, that you shrank the entire Milky Way to fit inside the area of a small country, say, Belgium, about 30,000 square kilometers, give or take. In that shrunken model, the Sun would be smaller than a grain of pollen. Earth would not be visible to the naked eye at all. The distance from the Sun to its nearest star would still be several kilometers, and the central black hole, Sagittarius A star, the heaviest single object in our galaxy, would be a pinhead-sized point somewhere near the middle, exerting almost no influence on anything you could see at that scale. That model still does not capture the emptiness. In any honest scale model of a galaxy, the stars are almost incomprehensibly far apart. The space between them, on average, is so vast that you could fly through a galaxy at speeds we cannot remotely achieve and pass through it without ever coming close to a single star. The galaxies you see in photographs, with their dense bright bulges and their crowded spiral arms, are a kind of optical compression. The light from billions of stars adds up to make the disk appear full, but on the actual scale the disk is mostly nothing, with stars scattered through it like very widely spaced grains of light in an enormous, mostly empty volume. This is the small one. This is the one most people picture when they hear the word galaxy. The familiar spiral. The pinwheel. The flattened disk with arms. There are 400 billion stars inside it, give or take. Roughly. Astronomers are not sure of the exact number because most of those stars are too faint and too distant to count one by one, even from the inside, so they estimate. The estimates run from 200 billion at the low end to 400 billion at the more commonly used middle. If you took every one of those stars and turned them into a single grain of sand, the pile of sand would be enormous. Several lifetimes of sand. Imagine the side of a beach. Then imagine more, and almost every one of those stars probably has at least one planet. The math is overwhelming on this point. We have searched a small portion of the Milky Way for planets, and we have found planets almost everywhere we have looked. The conservative estimate is that there is, on average, slightly more than one planet per star. That gives the Milky Way somewhere in the neighborhood of 400 billion planets. Maybe more. All of that. 100,000 light-years across. 400 billion suns. Hundreds of billions of worlds. And it is the small one. The galaxy we are going to walk toward tonight is more than 200 times longer than our own. That number is going to take a while to feel real. It is meant to. The whole script is going to be a slow approach to it. So before we leave the Milky Way, sit with the small one for a moment. Picture the dim band of stars that arcs across the summer sky in places far from city lights. That is the edge of our galaxy, seen from the inside. You are inside the picture you are looking at. You are looking out from the middle of an enormous slow wheel at the side of itself. It is already enormous. It is already so big that our minds cannot really hold it. And it is the small one. Let your shoulders drop for a moment before we go further. There is no rush. The largest galaxy will still be there when we arrive. The story of the largest known galaxy did not begin with a telescope launched into orbit. It began with a Hanoverian musician, working in England, watching a small patch of sky from the back of his house. His name was Frederick William Herschel, though most people, then and now, call him simply William Herschel. He was born in Germany in 1738, the son of a military oboist. He moved to England as a young man, made his living as a composer and music teacher, and only later in life turned his attention to the night sky. By the time he died, he had built some of the finest telescopes in the world, discovered the planet Uranus, identified moons, and catalogued thousands of objects nobody had ever recorded before. One of those objects, catalogued on the 19th of June 1790, was a faint patch of light in the constellation Serpens. He noted it, he recorded it, and then, like he did with most of his discoveries, he moved on. He had no idea what he had found. He could not have known. The very concept of a galaxy separate from our own did not yet exist. In Herschel's time, the working assumption was that everything in the sky was inside one single system, the same system the Sun and the Earth belonged to. The faint cloud he had spotted was, as far as he could tell, just another nebulosity. Another smudge in a long list of smudges. It would take more than 130 years before the rest of astronomy caught up with what he had been quietly looking at. In the 1920s, a different astronomer, Edwin Hubble, working with the new telescopes on Mount Wilson in California, finally proved that the soft clouds of the sky were not nebulosities at all. They were galaxies, separate islands, far outside the Milky Way, each one carrying billions of stars of its own. Once that was understood, Herschel's old smudges started being re-examined, one by one. Astronomers went back to the catalogues, pulled up the entries, and reclassified them as galaxies. The little entry from 1790, the one in Serpens, was given a new designation, IC 1101. The IC stood for Index Catalogue, a follow-up to an earlier catalogue of nebulae. The number was simply the number it landed on in the list, a name like a filing code. No grandeur, no drama, just an entry. But when astronomers measured how far away it was, and how wide it spread across the sky at that distance, something began to feel strange. The math kept getting larger. The galaxy was very far, and it was very wide. By the second half of the 20th century, IC 1101 was being mentioned with increasing seriousness as the largest known galaxy in the universe. Not by everyone, not without dispute. Galaxies are difficult to measure. Their edges are not crisp. They fade outward in soft halos that bleed slowly into intergalactic darkness. Where exactly you draw the line is, in part, a question of taste. But by whichever line astronomers preferred at the time, IC 1101 came out on top. It was big. It was strange. It sat at the heart of a particular galaxy cluster, more than 1 billion light-years away. And for the next several decades, when anyone asked the question we are asking tonight, this is the name that came up. It became the standard answer. It made it into the textbooks. It became one of those facts that astronomy students absorbed early, the same way they absorbed the planets in order, the way they absorbed the size of the observable universe, the way they absorbed the speed of light, the largest galaxy in the universe. IC 1101. For 2 centuries, give or take, this was the answer. And then, somewhere in the last 10 years, that answer quietly stopped being true. Not because IC 1101 shrank. It did not. It is still exactly where it has always been, doing exactly what it has always been doing. The galaxy has not changed. What changed is what we were willing to count. That is the central thread of the whole story, and we're going to come back to it many times tonight. The galaxies do not change. The ruler does. The question of which galaxy is the largest, depends entirely on what you decide to measure and how you decide to measure it. And every time we improve our instruments or our techniques, or even just our willingness to look at old data in a new way, the answer to that question moves. But before we get to the modern answer, we need to look more carefully at IC 1101, because the reason it still matters even after being overtaken is that it is still the largest galaxy in the universe by certain very real measures. The catch is in the word certain. Sit with that word for a moment, settle in. We're about to take apart the definition of size itself. Here is a question that sounds simple. How big is a galaxy? It is the kind of question a child asks. It has the same surface shape as how tall is a tree? The expected answer is a number measured in something familiar, with edges that everyone agrees on. The tree starts at the ground. It ends at the highest leaf. You take a tape measure or a laser and you record what you find. The tree is 23 meters tall. Done. A galaxy is not like that. A galaxy does not have a top and a bottom. It does not stop politely at a clear edge, it fades. The stars in the center are densely packed. The stars in the outer arms are more spread out, and beyond the arms, the density of stars keeps dropping and dropping and dropping until it's some quiet outer radius. You start losing count. There is no place where the galaxy ends and the empty space begins. The edge is a slope, not a line. So when an astronomer says a galaxy is 100,000 light-years wide, they are not quoting a measured boundary. They are choosing a definition. There are several to choose from, and each of them gives a different answer for the same galaxy. This is going to matter tonight, more than you might expect. The most common definition of a galaxy's size is something called the esophageal diameter. The word sounds harder than the idea. It just means you pick a brightness level, and you measure the width of the galaxy at the radius where the surface brightness drops to that chosen level. Different astronomers pick different brightness levels. So when one paper says a galaxy is 600,000 light-years across, and another paper says the same galaxy is 400,000, neither paper is wrong. They are using different rulers marked with different brightness lines. That is the first kind of size, the visible disk size. But the disk of a galaxy is not the whole galaxy. Around the disk there is usually a softer, dimmer envelope of stars called the halo. The halo is much harder to see because the stars in it are spread out, and because the light from the brighter disk often drowns out the halo around it. But the halo is still made of stars. It is still part of the galaxy. And the halo can be many times wider than the disk. So there is a second kind of size. The stellar halo size. Around the stellar halo, there is something even larger. Modern astronomy is fairly sure that nearly every galaxy is wrapped inside an enormous structure of a substance we cannot see directly, called dark matter. We do not know what dark matter is made of. We do not know its particles. But we can measure its effect on the motion of the visible matter inside the galaxy, and the effect is unmistakable. The galaxy spins as if it has many times more mass than its visible stars. The extra mass is dark. The dark matter halo of a galaxy can extend 10 times wider than its stellar disk, maybe more. So there is a third kind of size, the dark matter halo size. And then there is a fourth kind, the one that will matter most tonight. Some galaxies, especially those with very large central black holes, send out enormous jets of plasma into the surrounding space. These jets are not stars. They are not dust. They are not gas in the ordinary sense. They are streams of charged particles accelerated to nearly the speed of light, flowing out from the heart of the galaxy in opposite directions. After traveling for millions of light-years, the jets slow, spread, and inflate into immense lobes of glowing radio emission. These jets and lobes are also part of the galaxy. They are launched by it. They are powered by it. They are powered by it. They are connected to it. And in some galaxies they are by far the largest visible feature. So there is a fourth kind of size, the radio extent. Now consider what this means for our original question. Which galaxy is the largest? If you mean the largest by visible stellar disk, you get one answer. If you mean the largest by including the soft outer halo of stars, you get a different answer. If you mean the largest by dark matter envelope, you get a third answer that is harder to measure and easier to debate. And if you mean the largest by total extent, including the radio jets, you get yet another answer. And that answer can be many times larger than any of the others. This is the crack in the question, and it runs through everything that follows tonight. For most of the last 50 years, when astronomers ranked galaxies by size, they ranked them by stellar extent. That is the size you can see in visible light. That is the size you can photograph with optical telescopes. By that ruler, IC 1101 comes out on top, or very close to it. By that ruler, it is still the champion. Roughly 5.5 to 6 million light-years across, just in stellar light. Roughly 100 trillion stars inside that volume. By that ruler, IC 1101 is 50 to 60 times wider than the Milky Way. That is enormous. That is, by any ordinary use of the word, the largest galaxy that exists. But then in the early 2020s, the ruler quietly changed. A small team of European astronomers, using a particular kind of radio telescope, began doing something almost no one else was doing. They were not looking for stellar disks. They were looking for the faint, vast, mostly invisible plumes of plasma that some galaxies extend into the space around them. They were looking at radio extent, and when they switched to that ruler, the ranking shuffled, not by a small amount, by a factor of 3. Then by a factor of 7. Suddenly, IC 1101 was no longer the largest galaxy in the universe, not because it had shrunk. It had not. By stellar extent, it is still as large as ever, but by total extent, including the radio lobes that no one had been carefully measuring for decades, it had been quietly overtaken. This is the thing about size in cosmology. It is not always a property of the object. Sometimes it is a property of the question being asked. Take a breath. Let that sit. The room you are in is unchanged. The galaxies are unchanged. Only the way we measure them has shifted, and that small shift has rewritten what we believed for years. We are going to look at both rulers tonight, the stellar one and the radio one. The first one will take us through IC 1101 in proper detail, because by one perfectly valid measure, it is still the largest galaxy in the known universe. Then the second one will take us further than even that, into objects that, until very recently, nobody knew were galaxies at all. It is worth pausing for one more moment on this question of definition, because the looseness of the word size in cosmology is not a small technicality. It is a feature of how the universe is built. In everyday life, the objects you measure have crisp edges. A book has a clear boundary. A glass of water has a definite surface. A tree has a trunk, and even though the leaves at the top are a soft canopy, there is a height where the leaves end and the sky begins. The edges of normal objects are real, and the rulers we use to measure them work because the edges agree with the measurements. Galaxies do not behave like this. Almost nothing on cosmic scales does. The universe at large scales does not produce objects with clean boundaries. It produces objects with soft envelopes that fade into the surrounding medium across enormous distances. This is true of nearly every cosmic structure. Stars have atmospheres that thin out gradually into the surrounding interstellar medium. Star clusters fade outward into their host galaxies. Galaxies fade into their cluster halos. Clusters fade into the cosmic web. The web itself fades into the broader, large-scale structure of the universe. At every level, the boundary between inside and outside is a soft transition rather than a hard line. What this means in practice is that almost every cosmic measurement comes with a definition attached. When you read that a galaxy is so many light-years across, you should mentally insert the phrase by this particular convention. The convention matters. Different conventions give different numbers for the same object, and the differences can be large. This is not a flaw in cosmology. It is just the nature of the subject. The universe does not draw lines around things for our convenience. We draw the lines after the fact where they are useful. And when our understanding improves, we sometimes redraw the lines, and the answers shift. The story of the largest galaxy is, in a quiet way, a story about line drawing. Where do you put the edge of a galaxy? If you put it at the edge of the stellar disk, you get one ranking. If you put it at the edge of the stellar halo, you get another. If you put it at the edge of the radio emission, you get yet another. The galaxies have not changed. The lines have changed. The lines have changed, and with each change, the rankings move. That is the deeper lesson hiding inside the title of this video. The largest galaxy we have discovered is bigger than your imagination, but partly because the word largest is itself an expanding word. As we get better at measuring, the definition of size keeps getting larger. The frontier is in our methods, not just in the universe. There is no hurry. The night is long. To understand why IC 1101 held the title of largest galaxy for so long, you have to understand the place where it sits. It is not a lonely galaxy. It is not floating quietly through empty space. It sits at the very center of a galaxy cluster called Abell 2029, roughly 1 billion light-years from Earth. That cluster is one of the most massive structures in the part of the universe we can see from here. It contains thousands of galaxies bound together by their mutual gravity, slowly moving around a common center over timescales much longer than the age of human civilization. And right at the heart of that cluster, holding it together like a keystone, is IC 1101. Think for a moment about what that means. The cluster is not just a random collection of galaxies. It is a hierarchy. There are galaxies on the outer edges, smaller and dimmer. There are galaxies in the middle band, more numerous and brighter. And there is one galaxy at the absolute center. Larger than any of the others, brighter than any of the others, more massive than any of the others. That central galaxy is what astronomers call a brightest cluster galaxy, or BCG. And in Abell 2029, the BCG is IC 1101. When you look at a Hubble image of IC 1101, the first thing that strikes you is how unremarkable it looks at first glance. It is not a beautiful spiral. It is not a dramatic ring. It is an elliptical galaxy, which means it is roughly oval-shaped, dense in the middle, fading smoothly outward in every direction. The color is yellowish. The light is steady. It looks, in a quiet way, like a very large blurry circle of warm light, with smaller galaxies scattered around it like attendants. The unremarkable look is misleading. Inside that soft yellow blur, there are, by the best estimates, around 100 trillion stars. That is 1,000 times the number of stars in the Milky Way. If you took every grain of sand on every beach on Earth, the count would still fall short of the number of stars in this one galaxy by a fair margin. The light you see in the photograph is the combined glow of 100 trillion individual suns, each one with its own story, its own age, its own quiet population of orbiting worlds, and almost all of those stars are old. This is one of the strange features of giant elliptical galaxies. They are not making new stars at any meaningful rate anymore. The star formation in IC 1101 is essentially zero, or as close to zero as makes no practical difference. The galaxy is full of metal-rich stars that have been burning steadily for 7, 8, 10 billion years, and not many young blue stars to balance them out. That is why the light has a yellowish, settled quality to it. Yellow is the color of stars that have lived a long time. In a sense, IC 1101 is finished growing. Almost. It still pulls in material from the surrounding cluster, slowly. Astronomers estimate that the wider Abell 2029 cluster accretes roughly 450 solar masses of material every year, much of which eventually settles toward the center. So IC 1101 is not entirely static. It is feeding, just slowly, and mostly on the gravitational scraps of smaller galaxies that wandered too close and were absorbed long ago. That is the second strange feature. IC 1101 is so large because it has eaten other galaxies, many of them, over the billions of years that the Abell 2029 cluster has existed. Smaller galaxies have spiraled inward, been pulled apart by tidal forces, and had their stars scattered into the wider population of stars already orbiting the central galaxy. The result is that IC 1101 is not really a single original galaxy at all. It is a composite, the slow merger product of many smaller galaxies blended together into one enormous soft glow. That is why its core is the way it is. The core of IC 1101 is the largest galactic core ever measured. By the best estimates, the diffuse central region of the galaxy is about 13,000 light-years across, which is a remarkable structure in its own right. Inside that core, there is a supermassive black hole with a mass of somewhere between 40 billion and 100 billion times the mass of our Sun. That is among the most massive black holes known anywhere in the universe. So you have, sitting at the center of a galaxy cluster a billion light-years away, this object that is, by every measure that matters in optical light, enormous. 5.5 to 6 million light-years across. 100 trillion stars. A core larger than entire normal galaxies. A black hole so heavy that its event horizon, if you could stand outside it safely, would be larger than the orbit of Pluto by a wide margin. To stand inside IC 1101, hypothetically, would be a strange experience. The sky would not look like our sky. Our sky on a clear dark night is dominated by the band of the Milky Way, with individual nearby stars scattered across it, and a handful of fuzzy patches that, with binoculars, resolve into other galaxies far away. In IC 1101, the situation would be reversed. You would be embedded inside a galaxy whose stellar density is, at the center, far higher than ours. Your night sky might contain so many stars that the concept of a moonless dark night might not really apply. The combined glow of nearby stars would be bright enough that, at all hours, the heavens would have a steady, soft radiance. You might never see anything like the dim band of the Milky Way arcing across our summer sky. Your galaxy would not look like a band, it would look like the whole sky. And beyond your sky in every direction would be other galaxies of the cluster, close enough that some of them, the brightest of the surrounding members, might be visible to the naked eye as enormous diffuse patches, larger than anything we see in our own sky. The Andromeda Galaxy, our nearest large neighbor, is currently visible from Earth as a small dim oval about the size of the Moon on the sky. In Abell 2029, neighboring galaxies might appear far larger, brighter, more numerous, dominating sections of the night the way only the Moon dominates our own. It would not be a peaceful sky for an astronomer. There would be far too much going on. The kind of careful long-exposure observations we make from Earth, looking into deep dark space between bright sources, would be much harder. You would always be looking through stars, into more stars, with the next galaxy looming just behind. That is a thought experiment, of course. There are no astronomers in IC 1101, as far as we know. The galaxy is old. Its stars are old. Its star formation has been quiet for billions of years. If life ever began in that place, it would have had a very different stellar environment to work with than the one Earth has had. But the sky, if anything were looking up, would be a sky of overwhelming abundance, with little of the dark space that has made our own astronomy possible. And yet the more carefully astronomers measured it, the more they noticed something strange about that famous size. The outer regions of IC 1101, the parts that take it from a merely huge galaxy to the largest in the universe, are not bright. They are almost entirely halo, thin, diffuse, faint, spread across enormous volumes of space with very few stars per cubic light-year. Some astronomers have argued fairly that calling that faint halo a part of the galaxy is partly a matter of convention. The number you get for IC 1101 size depends heavily on how you treat the halo. Include it, and the galaxy is 6 million light-years wide. Cut it off where the surface brightness drops below a stricter limit, and the galaxy shrinks to 400,000 or 500,000 light-years, which is still enormous, but a fraction of the famous number. This is the first quiet reveal of what we said earlier. The galaxy has not changed. The ruler has. The size of IC 1101 is, in part, a function of where you draw the line. By the most generous ruler, the soft outer envelope still glowing dimly with starlight, IC 1101 comes out at around 6 million light-years from end to end. By that measure, it remains the galaxy with the largest known stellar extent in the universe. Nothing else anywhere that we have so far identified has a stellar population stretched across that wider region, so you should hold this in mind. As we walk forward into the rest of the story, into objects much longer than this one, IC 1101 does not vanish. It does not lose its title in every sense. It retains a very real one, the largest galaxy by stellar extent. the largest cathedral of stars we have seen. It is just that, in the last few years, we have discovered that some galaxies have reached far beyond their own stellar populations, and that is the door we are about to open. There is a particular kind of silence in astronomy that surrounds objects we do not yet know how to see. The universe is full of light that does not look like light to our eyes. Most of what reaches Earth from space is not visible. It is radio waves, microwave background, infrared heat, ultraviolet, X-rays, gamma rays, the narrow band of frequencies we evolved to detect, the band we call visible light, is a thin sliver in the middle of a much larger spectrum. If you imagine the full electromagnetic spectrum as a piano keyboard from one end of the room to the other, visible light is one or two keys near the middle. Everything else, the vast majority of the keyboard, is silent to our eyes. To see the rest of the keyboard, you have to build instruments. Different instruments for different bands. Optical telescopes for visible, infrared telescopes for heat, radio telescopes for the longer, slower wavelengths that ride on the bottom of the spectrum. Each one shows you a different version of the same sky. The optical sky and the radio sky are not the same picture. Many of the brightest objects in optical light are quiet in radio. Many of the brightest objects in radio light are nearly invisible in optical. If you put both sky maps side by side, they look like two different universes laid over each other, mostly overlapping, but with regions of strong disagreement. For most of the 20th century, the optical sky was where the famous galaxies lived. The Hubble Space Telescope made the optical sky beautiful in a way that no one had ever managed before. Pictures from Hubble found their way onto posters, school books, dorm room walls. Whole generations grew up associating the word galaxy with the kinds of objects Hubble could show: spirals, ellipticals, clusters, the optical sky. The radio sky was quieter. The discoveries it produced were often more technical, harder to picture, easier to bury inside a journal article. Radio astronomers had been finding strange and gigantic objects in their data for decades, but those objects rarely made it into the popular imagination, because radio images do not photograph well. They are diffuse, soft, sometimes lumpy, sometimes ghostly. They do not look like galaxies, even when they are. This is the band of the spectrum where the story we are about to tell unfolds. In the Netherlands, near the city of Drenthe, there is a radio telescope unlike most others in the world. It is not a single large dish. It is a network. Thousands of small antennas spread across the countryside, connected together by fiber optic cable, all combining their signals to act, in effect, as one enormous telescope. The name of the system is the Low Frequency Array, abbreviated LOFAR. It listens to a band of the spectrum that almost no other major facility on Earth covers in detail. Long wavelengths, low frequencies, the deep bass of the sky. LOFAR has been sweeping the northern sky steadily for years, building a survey that astronomers call LOTSS, the LOFAR 2-meter sky survey. The survey was not designed with one single target in mind. It was designed to map, to listen broadly, to catalogue, and in the data of that survey, hidden in plain sight, were galaxies whose true sizes nobody had yet measured. The reason is interesting and worth slowing down on. The radio lobes of a galaxy, when they grow very large, become very faint. The plasma in them spreads out across enormous volumes of space, and the light each cubic light-year of plasma emits gets dimmer and dimmer. By the time the lobes are a few million light-years long, they are so diffuse that ordinary radio survey images barely register them. The signal is there. It is just buried under noise and the brighter compact sources around it. If you want to see those faint outer lobes, you have to do something patient. You have to take the survey data, subtract out all the bright point-like sources, smooth what remains, and look very carefully for soft, large-scale patterns in the background. Most people do not do this. It is slow work. It does not lead to obvious headlines. The brighter targets in the survey are more rewarding to chase. But a small team in the Netherlands began doing exactly this. They were not hunting for the largest galaxy in the universe. They were investigating, in a fairly technical way, what they called giant radio galaxies, a class of objects defined by jets longer than about 2.3 million light-years. The definition was already large, They were looking for the bigger members of that class to understand what set them apart. So they took the low TSS data, reprocessed it, smoothed it, looked at it with new eyes. What they found was that the data was full of these giants, not one or two, many. Galaxies whose radio extents reached far beyond anything that had been catalogued before, giant after giant after giant. All of them faint, all of them previously unmeasured, all of them sitting quietly in survey images that nobody had bothered to reprocess at this level of care. The first time anyone publishes a result like this, the immediate question becomes, which one is the largest? In a field full of giants, who is the king of the giants? That question has a name now. It was answered in early 2022, and the name of the answer was something out of mythology. But before we say it, sit with the moment of discovery itself, because it is one of the quiet beauties of modern astronomy. The galaxy that took the record for largest in the known universe was not found because someone built a more powerful telescope. It was found because someone looked at the old data more carefully. The image had been taken years before. The plasma plumes had been faintly visible the entire time. What changed was a method, a willingness to subtract the bright sources, a willingness to look at what remained. The galaxy had been sitting in the sky for billions of years. Its light had been reaching Earth the whole time. It was already in the data. It had simply been hiding under the noise of everything else. That is one of the deeper lessons of this story. The universe is not always discovered. Sometimes it is finally noticed. Let your shoulders drop. We are about to meet the giant. The name they gave it was Alcyoneus. In Greek mythology, Alcyoneus was one of the Gigantes, the giants who rose against the Olympian gods and fought Hercules for control of the cosmos. He was a son of Erenos, the primordial god of the sky. The name was chosen, the discovery team said, because the object they had found in their data was so far beyond the size of anything previously known that calling it merely large felt inadequate. They needed a mythological scale. The proper galaxy that hosts Alcyoneus has a less poetic name. It is catalogued as SDSS J08 1421.68 plus 5 22410.0.0.0. The string of digits encodes the galaxy's position on the sky. It is an elliptical galaxy, much like IC 1101, sitting roughly 3 to 3.5 billion light-years from Earth, in the constellation of Lynx. Lynx is one of the lesser-known constellations. It was created in the 17th century by the Polish astronomer Johannes Hevelius, and his joke, when he named it, was that you would need to have the eyes of a lynx to see most of the stars inside it. They are faint. The constellation is a quiet patch of the northern sky well above the bright bowl of the Big Dipper. Easy to miss if you are not looking for it. That is where Alcyoneus lives, hidden in the soft glow of one of the dimmer constellations in the sky. The team that found it was led by a Dutch graduate student named Martijn Oei. At the time, he was completing his PhD at the Leiden Observatory in the Netherlands. The Leiden Observatory is one of the oldest astronomy departments in the world, founded in 1633, and it has a long tradition of careful radio work. Oei and his colleagues, working with collaborators from Hertfordshire and Oxford in the United Kingdom and from Paris in France, published their result in February of 2022 in the journal Astronomy and Astrophysics with the unassuming title, The Discovery of a Radio Galaxy of at least 5 megaparsecs. The title is a measurement. 5 megaparsecs is the technical way of writing the distance, in the units astronomers actually use among themselves. This paper was an announcement that somewhere in the data was a single galactic structure stretched across at least 16.3 million light-years. That is the number worth pausing on. 16.3 million light-years. 5.04 megaparsecs, give or take. End to end. Take the Milky Way at 100,000 light-years across. Then line up another beside it. Then another. Then another. Beside it. Then another. Then another. Keep going. You would have to set down 160 Milky Ways, end to end, before you reach the length of Alcyoneus. For context, IC 1101, the previous record holder, was about 6 million light-years wide at its most generous measurement. Alcyoneus is roughly 2.5 times longer than that. The jump in scale is enormous. It is not a small revision of the old record. It is a different scale entirely. That is the climax of the modern story, and it deserves to be felt for a moment rather than measured. From the moment you hear the title of this video, you are waiting for a number. The number arrives here, 16.3 million light-years. The largest galaxy in the known universe as understood between 2020 and 2024. How do you picture something like this? You do not really. The number is too far outside the range of human experience to be visualized in any honest way. What you can do is hold it gently in mind as a fact and let the rest of the script slowly fill in what kind of object can possibly be that long. Because that is the strangest part of all. Alcyoneus is not a uniformly bright stellar disk that wide. It is not a wall of stars stretching across 16 million light-years. The galaxy itself, the part with stars in it, the part that looks like a normal elliptical galaxy in optical light, is much smaller. A few 100,000 light-years across at most, like other large ellipticals. The 16 million light-years is the radio extent, the plasma plumes, the jets and lobes that emerge from the host galaxy and stretch for millions of light-years on either side into the surrounding intergalactic space. That is what makes Alcyoneus, by the modern definition, a galaxy. Not just a galaxy, but the largest one. The structure as a whole, from the leading edge of one radio lobe through the central host galaxy to the leading edge of the opposite radio lobe, spans 16.3 million light-years of physical space. If you stood on a planet inside the host galaxy at the center of Alcyoneus and looked outward, you would see ordinary stars, much like the stars in our own night sky. You would have no idea from the view from your imagined window that your galaxy was famous. The famous part of Alcyoneus is mostly invisible. It glows in radio wavelengths only. To the eye, it is just another dim elliptical, like millions of others in the catalogues. You can only see Alcyoneus correctly if you can see in radio. To LOFAR, Alcyoneus is huge. It takes up nearly 21 arc-minutes on the sky, which means it looks about as big as the moon does to your eye. That is one of the strangest details of the entire story. A galaxy 3 billion light-years away looks, in the radio sky, about the size of the moon. Most galaxies of that distance look like dots, indistinguishable from points. Alcyoneus looks like the moon. Hold that comparison gently. Imagine on a clear night, looking up at the full moon. Now imagine that you are not looking at the moon, you are looking at a single galaxy, the same apparent size, but billions of times further away and longer than 160 Milky Ways set end to end. That is what Alcyoneus is. When the paper was published, the immediate question astronomers asked was, how is this even possible? Galaxies were not supposed to grow this long. The theoretical models of galaxy formation had not really allowed for it. Something about the conditions around Alcyoneus, or something about the host galaxy itself, was producing a structure larger than the calculations had predicted as possible. The answer to that question is what the rest of the script is going to walk through. There is a mechanism behind the size, and it is one of the more elegant ones in cosmology. It involves black holes, magnetic fields, and the strange way matter behaves when it is accelerated to nearly the speed of light. We will get there slowly. For now, sit with the number. 16.3 million light-years. The largest galaxy in the known universe, as the world understood it from February of 2022 until September of 2024. That qualifier matters. We will come to it. But not yet. Let your breath slow. The walk is not over. We are halfway across. There is a small detail in the discovery story that the published papers describe almost in passing, but that is worth slowing down on because it captures something about modern astronomy that is easy to miss. The team did not discover Alcyoneus all at once. The discovery happened in stages over a period of weeks. Oei and his colleagues had been reprocessing portions of the LUTSS survey data, looking for radio galaxies whose extents had been underestimated in the original survey images. They had developed a technique for subtracting the bright compact sources and smoothing what remained, allowing the faint diffuse plumes of large galaxies to show up against the residual background. At first, they were finding interesting candidates, larger than the average, worth following up. But not record-breaking. The work was steady, careful, somewhat repetitive. Most days you look at the data, you flag a candidate, you measure it, you move on. Then, on one particular run through a particular patch of sky in the constellation Lynx, the residual image showed something that did not look like an ordinary giant radio galaxy. The lobes, when measured, extended across an arc of the sky larger than anything they had previously catalogued. The host galaxy in the middle was small, ordinary, unremarkable. The plumes on either side reached for what, when distance and angle were taken into account, would have to be more than 5 megaparsecs in total length. That is the moment in the story. Somebody, in a quiet office in Leiden, looked at an image on a screen and realized that the number they were about to write down was larger than any number ever recorded for a single galaxy. The realization was probably quiet. Astronomers by temperament are cautious. The first response to a measurement like that is not excitement, it is doubt. You look at it again, you check for processing artifacts, you remeasure, you ask whether the structure is really a single coherent jet system, or whether it might be two unrelated objects that happen to line up by chance. You go through the checklist. In the case of Alcyoneus, the checks held up. The structure was real. The two lobes were physically connected through the central jet to the same host galaxy. The redshift of the host placed it at the proper distance, allowing the apparent angular size to be converted into a real physical extent. The number stayed where it was, 16.3 million light-years. That is what discovery looks like in modern astronomy. Not a sudden gasp at a telescope eyepiece. A careful, slow, weeks-long process of measurement and verification, ending in a number that, when finally written down for publication, you have triple checks and asked 3 skeptical colleagues to argue against. The number was right. The paper was submitted. The journal accepted it. The world learned about Alcyoneus a few months later. But the moment, the actual moment of recognizing the giant, happened quietly in front of a computer with no audience. That is true of almost every modern astronomical discovery worth remembering. The universe reveals itself to the patient in the privacy of careful work on ordinary afternoons. Almost every large galaxy in the universe has a supermassive black hole at its center. This is one of the more recent realizations of modern astronomy, and it took a while to settle. The first hints came in the 1960s, when astronomers noticed that the centers of some galaxies were strangely bright, with concentrated radio emission and rapidly moving stars and gas clouds. By the 1990s, the case was strong. By the 2010s, it was effectively settled. If a galaxy is large enough, somewhere in its core there is a black hole of millions, sometimes billions of solar masses, sitting at the center of the gravitational well. The Milky Way has one. Its name is Sagittarius A star, written A and an asterisk, pronounced just like it looks. It is about 4 million times the mass of the Sun. By the standards of cosmic black holes, it is not enormous. There are many far heavier, but it is ours. It sits at the center of our galaxy, and our entire stellar disk slowly turns around it, one revolution every 220 million years or so. A black hole on its own does not produce a giant radio galaxy. Most black holes are quiet. They sit at the centers of their galaxies, slowly absorbing material that drifts too close and emit relatively little in return. The Milky Way's black hole is quiet by current standards. There is no enormous jet pouring out of the center of our galaxy. There has been in the past evidence of more active phases, but right now things are calm. The black holes that produce the giant radio galaxies are not calm. When a supermassive black hole begins feeding actively, when streams of gas and dust spiral in toward its event horizon at a steady rate, several things happen. The infalling material does not flow in smoothly. It piles up into a flat structure called an accretion disk, swirling around the black hole at enormous speed. Friction inside the disk heats it to extreme temperatures. Magnetic fields, threaded through the spinning plasma, get twisted and amplified into structures of fearsome power. And along the spin axis of the black hole, in the two directions perpendicular to the disk, something escapes. The escape is not gentle. It takes the form of two narrow, collimated beams of charged particles, accelerated to nearly the speed of light, launched out of the central region of the galaxy along the axis of rotation. These are the jets. They are not metaphorical. They are physical streams of matter and electromagnetic field, leaving the host galaxy at relativistic speeds, traveling outward into the wider universe. Once the jets leave the galaxy, they keep going. They do not stop at the visible edge of the host. They do not stop at the edge of the stellar halo. They keep streaming outward, propelled by the same physics that launched them for millions of years, sometimes tens of millions, sometimes longer. Eventually, after traveling for an enormous distance, the jets begin to slow. The plasma in them spreads out, decelerated by the resistance of the very faint intergalactic gas they push against. As they slow, they inflate. They become wider, more diffuse, more lobe-shaped. The energy carried by the original beam gets distributed across a much larger volume. The two ends of the structure, far from the original galaxy, swell into immense glowing balloons of relativistic plasma, emitting radio waves through a process called synchrotron radiation. This is what you see when you look at a giant radio galaxy. Not really a galaxy in the usual sense. A central galaxy, normal-sized, with two long jets emerging from its core, and two enormous radio lobes at the ends of those jets, far out in intergalactic space. The Milky Way has small versions of these features. Most galaxies do. Even a quietly behaved galaxy has detectable radio lobes, called the Fermi bubbles, extending some 25,000 light-years on either side of the galactic plane. They are real. They are present. They are visible in the right wavelengths. They just happen to be modest, on the scale of our own galaxy. In the giant radio galaxies, the mechanism is the same. The scale is different. For reasons we do not yet fully understand, the jets in some galaxies grow far longer than usual. Most radio galaxies produce lobes of a few 100,000 light-years, sometimes a million, which is already huge. The ones we call giant radio galaxies, by formal definition, have lobes longer than about 2.3 million light-years from end to end. There are thousands of these known. A few of them, the rarest, extend longer still, tens of millions. The reasons for this extreme growth are still being studied. Parts of it has to do with the environment around the host galaxy. The jets travel further when the surrounding intergalactic medium is unusually thin, with very little gas to push against. Part of it has to do with the host galaxy's properties. Certain kinds of central black hole behavior produce more stable, longer-lived jets than others. And part of it probably is age. A jet that has been running steadily for 100 million years will simply extend further than one that started 10 million years ago. Alcyoneus by this physics is what happens when you put together a particularly massive central black hole, an unusually thin intergalactic environment, and a remarkably steady period of jet activity, lasting for what may be hundreds of millions of years. The result is two of the longest plasma plumes ever detected, with the host galaxy quietly sitting at the center, smaller than its own jets by orders of magnitude. That is the mechanism. That is what makes a galaxy this large. It is not, in itself, an exotic process. There is no new physics in Alcyoneus. The black hole is a normal supermassive black hole. The jets are normal accretion-powered jets. The radiation is normal synchrotron radiation. Every step of the process is one we already understand from smaller examples. What is unusual is the scale, the willingness of the universe, in this particular case, to let the jets keep growing and growing and growing until the structure reaches 16 million light-years from one end to the other. There is something quietly humbling about that. The Milky Way, which feels so enormous from where we sit inside it, has all the same machinery: a central black hole, a faint pair of radio lobes, an accretion history, quiet versions of all of it. We have, in a sense, the same equipment as Alcyoneus. We just operate at a different volume. In another version of the universe with our central black hole a bit hungrier, our magnetic fields slightly more cooperative, and our surroundings a touch thinner, the Milky Way might also have grown jets long enough to span millions of light-years on each side. It did not. It does not. But the machinery is there. When you understand this, the largest radio galaxies stop feeling like exotic monsters. They start feeling like turned-up versions of the galaxies we know. Same instruments, same physics, more volume. Take a slow breath. Let the picture settle. There is one more piece of the Alcyoneus story that is worth sitting with before we move forward. When the Discovery team looked carefully at the plumes of Alcyoneus, they noticed something that took them by surprise. The plumes were not straight. They were not perfectly symmetric. One side bent gently in one direction. The other side bent in a slightly different one. The lobes had a soft, asymmetric, almost wind-blown shape, as if something invisible had been pushing against them as they grew. That observation was not a problem. It was a clue. The intergalactic medium, the very thin gas that fills the space between galaxies, is not perfectly uniform. It has currents. It has densities. Some regions are slightly thicker, others slightly thinner. When a jet of plasma travels for millions of light years through this medium, the medium pushes back, not strongly because the gas is incredibly faint, but over enormous distances and enormous time spans, even faint pushing adds up. The plume curves. The lobe bends. The galaxy ends up with a shape that reflects, in soft curves, the slow currents of the matter it is moving through. The Alcyoneus team described this poetically. The plumes, they said, were dancing with an invisible partner. The intergalactic medium was their partner. The plumes were big enough, soft enough, slow enough, that they responded to the medium's currents in a way smaller jets do not. Think about what this implies for a moment. A galaxy whose outer regions are shaped not by its own gravity, not by its own internal structure, not by the orbits of its own stars, but by the empty space around it. The largest features of Alcyoneus are sculpted by the thinness of the medium they pass through. The form of the galaxy is, in part, a sculpture by emptiness. That is one of the quiet philosophical edges of this story. The largest known galaxy is also, in a sense, the most porous. Its visible extent is mostly determined by where the surrounding void allows it to be. Move the same galaxy to a slightly denser region of space, and its plumes would be shorter, more compressed, less wide. Move it to a thinner region, and it might be longer still. The galaxy is not just an object, it is a relationship between an object and its environment. The implication of this, for the field of astronomy, is more practical and more interesting. It means that the giant radio galaxies are also, in effect, very large probes. Their plumes register the density of the intergalactic medium they push against. If you can map the shape of the plumes, you can begin to map, indirectly, the structure of the medium itself. The thin gas between galaxies, which is otherwise nearly impossible to image at all. The intergalactic medium is one of the most poorly mapped substances in modern cosmology. It contains, by estimate, a large fraction of all the ordinary matter in the universe, most of the hydrogen, most of the helium, the vast majority of the visible material. But because it is so thin and so faint and so cold in most places, we cannot photograph it directly. We can only infer it, slowly, from its effects. The giant radio galaxies are one of the rare windows into that hidden substance. Their plumes feel the medium. Their shapes record it. They are, in a literal sense, instruments built by black holes and used to map the most invisible parts of the universe. That is a very different way of looking at what Alcyoneus is. It is not just the largest galaxy. It is a kind of cosmic probe. It is matter that was launched from a supermassive black hole hundreds of millions of years ago and is now drifting through the empty regions between galaxy clusters, slowly responding to the gravitational and pressure fields of the medium it passes through, slowly turning into a record of those fields. When you look at a radio image of Alcyoneus, you are not just looking at a galaxy. You are looking at a slow-motion experiment in fluid dynamics on cosmic scales, running for hundreds of millions of years, with the plumes themselves as the readout. This is what astronomy increasingly looks like at the highest levels, not single objects in isolation. Relationships. Patterns. Structures that respond to their environments. Galaxies, in this view, are not closed systems, they are open, they send things out. The things they send out interact with the wider universe. The shape that comes back is the shape of that interaction. Hold this for a moment because it changes what the largest galaxy means. If a galaxy was simply a closed island, then asking which galaxy is the largest would be like asking which mountain is the tallest. A clear, bounded question with a clear, bounded answer. But if a galaxy can extend itself outward by tens of millions of light years through jets and plumes, and if those plumes are shaped by the medium they travel through, then the question of size becomes a question of reach. How far does a galaxy reach? How far does its influence travel? How far do its jets push before they fade into nothing? Those are the new questions, and the answers for the largest known galaxies are extending steadily outward every time someone reprocesses an old survey or takes a new one with better sensitivity. The plumes of Alcyoneus reach for 16 million light-years. They drift through the intergalactic medium. They bend gently with its currents. They mark, in radiolight, the shape of nearly empty space. Let your shoulders drop. Settle. We are about to meet the galaxy that overtook even this. For 2.5 years, Alcyoneus held the title. From February of 2022 until September of 2024, when anyone asked the modern question, what is the largest galaxy in the known universe, the answer was Alcyoneus, 16.3 million light-years from end to end. The first member of the modern era of giant galaxy records. A creature of plasma and patience hidden in old data, finally seen properly. And then, in the autumn of 2024, the same team that found Alcyoneus published a new paper in the journal Nature. They had been continuing their work, reprocessing more LOFAR data, looking for more giants in the LOTSS survey with the methods they had developed. They were no longer simply asking whether bigger ones existed. They were asking how big the biggest one could possibly be. The answer they found has a name from Greek mythology too: Porphyrion. Like Alcyoneus, Porphyrion was one of the Gigantes, a giant who rose against the gods. The name was chosen again because the object the team had found was so large that it required the language of myth to label it. The first paper had used Alcyoneus. The new paper used Porphyrion. There are more giants in the myths. The implication is gentle but clear. The record may not stop here. The host galaxy of Porphyrion has the catalogue naming J1 529 32 93 2.16 plus 60 153 4.4. The numbers, once again, in code positioned. It sits in the constellation Draco the Dragon, which winds through the northern sky around the celestial pole. Draco is a much larger constellation than Lynx, and a more famous one. The pole star itself, Polaris, is close to its boundary. So somewhere in Draco, hidden among the dimmer stars, there is a faint elliptical galaxy. And from that elliptical galaxy, in two opposite directions, plasma plumes extend outward for an enormous distance. How enormous? 23 million light-years, 7 megaparsecs, 7.3 according to some measurements. Roughly half again as long as Alcyoneus, roughly 4 times longer than the stellar extent of IC 1101. So long that, when you line up Milky Ways end to express it, the number is no longer 160. It is 140. 140 Milky Ways set in a row touching at the edges before you reach the other side of Porphyrion. Let the number sit. Take a breath. It is, at this scale, almost meaningless to try to picture. You cannot. Nobody can. The galaxy is so long that even astronomers, when they write about it, often pause to acknowledge that the human imagination is not equipped for the scale. The lead author of the discovery paper, Martijn Oei, the same researcher who had led the Alcyoneus discovery, was by now a postdoctoral scholar at the California Institute of Technology, Caltech. He commented at the press conference that the Milky Way, set inside Porphyrion's plumes, would be a little dot. The dot is so small it is the wrong word. It is more like a speck. That is the modern record holder. As of the publication of the Nature paper in September of 2024, the largest galaxy in the known universe by total physical extent is Porphyrion. 23 million light-years long, 140 Milky Ways across. And there is a further detail mentioned in the paper that is worth lingering on for a moment. Porphyrion is what is called a Phaneroff-Rayleigh class 2 radio galaxy. The name comes from a classification system developed in the 1970s by two astronomers named Bernie Phaneroff and Julia Riley. They noticed that radio galaxies came in two basic flavors. In one, the jets are bright near the host galaxy and fade outward as they travel. In the other, the jets are quieter near the host, but flare into bright hotspots at their distant ends, far from the central galaxy. The first kind they called Class 1. The second kind they called Class 2. Alcyoneus is a Class 2. Porphyrion is also a Class 2. This matters because Class 2 jets are the ones that carry energy far out into intergalactic space, depositing it at their distant ends. They are the long-reach varieties. They are the ones that touch regions of the universe far beyond their host galaxies. They are the ones that, if they exist at all, can stretch on for millions of light years. Porphyrion is one of these. The energy in its hotspots at the far ends of its plumes is enormous. The total power output of the jet system, integrated over its entire structure, is comparable by some estimates to the brightness of trillions of suns. It is one of the most luminous in radio wavelengths of any galactic structure ever measured. That energy is leaving the galaxy. It is being deposited into the wider universe. Stop and consider what that means. A single supermassive black hole, somewhere in the constellation Draco, has been quietly running an engine for what may be hundreds of millions of years. The output of that engine has reached, by now, 23 million light-years from the source. It has carried energy that far. It has carried magnetic fields that far. It has carried plasma that far. The reach of this one galaxy, defined honestly by where its influence extends, covers a region of intergalactic space larger than any single galaxy known. The Caltech team described this in their press materials with a phrase that quietly raised the stakes of the entire field. Porphyrion, they said, is the first known black hole jet that operates on the scale of the cosmic web itself. That phrase needs unpacking because the cosmic web is one of the deepest discoveries of modern cosmology, and most people have only heard it in passing. The universe, on its largest scales, is not uniform. Galaxies are not scattered randomly through space like grains of sand on a beach. Instead, when you map the locations of galaxies across very large volumes, you find a structure. The galaxies cluster along filaments. The filaments stretch across hundreds of millions of light-years, meeting at nodes where dense clusters of galaxies sit. Between the filaments are huge regions of nearly empty space called voids. The whole pattern resembles, when imaged at the right scale, a vast three-dimensional web. Cosmologists call it the cosmic web, and it is the largest known organizing pattern in the universe. The filaments of the cosmic web are typically tens of millions of light-years thick. The voids are tens to hundreds of millions of light-years across. Until recently, the assumption was that galaxies operated mostly within their own immediate neighborhoods, with their gravity and their jets affecting at most their nearest few neighbors. The scales of the cosmic web were thought to be too large for any individual galaxy to influence directly. Porphyrion changes that assumption. A galactic jet system 23 million light-years long is, in physical terms, comparable in scale to a thick filament of the cosmic web. The plumes of Porphyrion are no longer just inside their host galaxy's neighborhood. They reach across regions large enough to interact with the web itself. The energy they deposit is being added to the wider intergalactic medium in volumes that matter on cosmic scales. That is genuinely new. The Discovery team described it in the paper as evidence that supermassive black holes can influence not just their host galaxies but the cosmic structure surrounding them. It is one of the few times in modern astronomy when the words paradigm shift have appeared, quietly, in serious peer-reviewed work. So that is Porphyrion. 23 million light-years. 140 Milky Ways, the largest known galaxy in the universe, as of the time of writing this script. A creature whose jets reach into the very pattern of the cosmic web. A black hole engine running for hundreds of millions of years, depositing its energy at distances we did not know any single galaxy could reach. And the strangest part is that it has been here, in our sky, the entire time. To make Porphyrion feel a little less abstract, it helps to compare it to other jet systems that we already know. The nearest galaxy with a large jet system is Centaurus A in the southern constellation of Centaurus. It is one of the closest active galaxies to the Milky Way, about 13 million light-years away. Its jets, by cosmic standards, are well studied. They extend across about 1 million light-years from end to end, which is itself an enormous structure, larger than 10 Milky Ways laid in a row. A few years ago, astronomers studying a different jet system around a galaxy called NGC 263 in the same general region of the southern sky found that its jets extended even further, roughly 10 times the diameter of the Milky Way. That was, at the time, considered a remarkably large pair of jets. It was the subject of a major paper. It made headlines. Porphyrion's jets are larger than the NGC 263 jets by a factor of more than 20. That is the scale of the jump, 20 times the size of what was considered a major discovery in the early 2020s, 140 times the diameter of our home galaxy, multiple times the size of even the most extended radio structures previously found in the LOFAR data. The lead author, in describing the result, said simply that this pair of jets is not just the size of a solar system or even a Milky Way. It is on the scale of 140 Milky Way diameters in total, with the Milky Way itself being a tiny dot somewhere inside the structure if it were placed there. The dot, again, is the wrong word. The Milky Way would be a faint speck against the enormous luminous extent of the plumes. There is one more piece of context worth adding. The total energy output of Porphyrion's jets, integrated over their entire structure, has been estimated to be roughly equal to the energy output of trillions of suns, not trillions of stars, all at once. The energy delivered continuously by the single accretion-powered jet system at the center of the host galaxy over the course of its operation. The host galaxy, in its individual starlight, is unremarkable. The jets it produces dwarf the luminosity of the galaxy itself by enormous factors. This is the strange inversion of the giant radio galaxies. The galaxy you can see in optical light is a normal-looking object. The galaxy you can see in radio is a beast on the scale of cosmic structures. The same object in two different parts of the spectrum presents two completely different scales of itself. Optical Porphyrion is small. Radio Porphyrion is enormous. They are the same galaxy. There is one more layer to Porphyrion that is easy to skip past, but that quietly changes everything. When you read that Porphyrion is 23 million light-years long, you might assume, naturally, that this is what the galaxy looks like right now, that somewhere out there, in the present moment, a jet of that length is currently extending into space. That if you could somehow look at the galaxy live, you would see what we just described. That is not what the data shows. Porphyrion is approximately 7.5 billion light-years from Earth. That number is not just a distance, it is also a time. Light travels at a finite speed. The image of Porphyrion that LOFAR captured did not leave the galaxy yesterday. It left more than 7 billion years ago, and has been travelling toward our solar system ever since crossing the universe at the speed of light, only arriving in the last few years, in the radio waves now being processed by computers in the Netherlands. What we are seeing in the data is Porphyrion as it was, not as it is. When the light from Porphyrion's plumes left the galaxy, the universe was about 6.3 billion years old. That is less than half the current age of the universe. Our sun did not yet exist. Earth did not yet exist. There would not be a planet in this neighborhood of the Milky Way for another 2 billion years. Life on Earth, when it eventually emerged, would still be more than 4 billion years in the future. Porphyrion, as we see it, is older than half the universe. Its image is older than our planet by more than 2 billion years. Its light has been in transit for longer than there have been continents on Earth. Hold that gently because it changes how you should feel about the image. The galaxy you have been picturing in this script, the long thin structure of plasma plumes stretching for 23 million light-years across the constellation Draco, is, in the present moment, almost certainly different. The black hole at its center may have stopped its active phase. The jets may have faded. The plumes may have dissipated into the cosmic medium, or alternatively the engine may have kept running. and the jets may now be even longer than what we are seeing. We do not know. We will not know. The light that would tell us has not yet arrived. What we are looking at in any image of Porphyrion is a fossil, a snapshot of an event that finished or did not finish billions of years ago, travelling slowly toward us through the dark. This is true of nearly every distant galaxy. We see them all as they were. The most distant galaxies in the deep field images are baby galaxies, glimpsed when the universe was a few 100 million years old. The closer galaxies are older, but still not quite present. Even Andromeda, our nearest large neighbour, appears to us as it was 2.5 million years ago, when early humans were just beginning to walk upright on the African savanna. The night sky is, in this sense, a slow-motion archive. The further you look, the further back in time you see. There is no way to see the universe as it is right now. There is only the universe as it was, layered together, with closer events on top and more distant events underneath. When you understand this, the question of which galaxy is the largest gets stranger, because the largest galaxy we have ever seen, Porphyrion, may not be the largest galaxy that exists right now. Right now, somewhere in the universe, there might be other galaxies whose jets have grown longer than Porphyrion's were when its image left. We will see them, eventually, when their light reaches us, billions of years from now. Some of them, of course, also will not exist anymore by the time their image arrives. The mat is always old. The territory is always somewhere else. This is the deep time reframe that comes with the title of largest. It is a tense problem. Largest when? Largest as seen from where? Largest along what slice of cosmic history? In practice, when astronomers say largest, they mean largest in the catalogue of currently known galaxies, regardless of when their light left them. That is the only practical definition. We cannot rank galaxies by their current state because we do not have access to their current states. We rank them by what we can see. And what we can see, at the moment, has Porphyrion at the top. Sit with the picture for a second. A galaxy more than 7 billion light-years away, whose plasma plumes were already 23 million light-years long when our solar system was still a swirl of dust around a young star, whose image was already in transit when the first cells on Earth began to divide, whose light has been moving steadily across the dark of intergalactic space for longer than there have been multicellular animals. When LOFAR captured that light, it captured something very old. When the researchers reprocessed the data and noticed the plumes, they were not just discovering a galaxy, they were receiving a message from a structure that had been making its journey toward them for most of the history of the universe. The strange softness of cosmology comes from this. Everything you look at, you see late. The further out, the later. The universe is not a thing that you stand outside of and examine. It is something you are inside of, and what you see depends on where you stand and how long ago the light was sent. Let your shoulders drop. Take a slow breath. We are not finished yet. There is more to say about Porphyrion and about what comes after Porphyrion. But before we move forward, let the image settle. The largest galaxy we have ever seen. Almost certainly not exactly the largest one out there. Almost certainly not exactly what it looks like in the data. But the largest one we have in the only catalogue we are allowed to keep. Porphyrion's size is not just a record. It is a problem. For most of modern astrophysics, there has been a quiet theoretical limit on how large the jets of a radio galaxy can grow. The limit is not arbitrary. It comes from the physics of how the jets propagate through space. Jets push against the surrounding medium. The medium pushes back. As a jet extends further from its host galaxy, the medium becomes more resistant, in part because the jet has slowed, and become more vulnerable to disruption, and in part because the medium itself can vary in density at large scales. The traditional rule of thumb, derived from decades of modelling and observation, was that radio jets could grow to a length comparable to about 1/4 the diameter of a typical cosmic void. Beyond that scale, the jets were expected to lose coherence, to become disrupted, to dissipate. Cosmic voids, the large empty regions between galaxy filaments, are typically tens of millions of light-years across. A quarter of that gives you several million light-years, maybe 10 million in the more generous cases. That was the working limit. The largest known jets before the modern era fit comfortably under it. Alcyoneus already pushed the limit. 16 million light-years was at the upper edge of what the old models comfortably allowed. The Discovery teams noted in their paper that their findings suggested either the cosmic voids were larger than expected, or the jets were behaving in ways the models did not capture. There was a hint in 2022 that the limits would have to be reconsidered. Porphyrion broke them. 23 million light-years is well beyond what the old models predicted as possible. It is well beyond a quarter of a typical cosmic void. It is, in some directions and in some environments, approaching the scale of the cosmic web filaments themselves. A jet that long has, by the traditional understanding, no clear right to exist. It should have disrupted. It should have spread out into incoherent plasma long before reaching its current extent. But it did not. There are several proposed explanations, and the field is still working through them. We do not have a settled answer. What follows is the best honest summary of where the thinking currently stands. One possibility is that the environment around Porphyrion's host galaxy is unusually empty. Even by the standards of cosmic voids, certain regions of the universe are thinner than others. If Porphyrion's jets happen to extend in a direction where the intergalactic medium is particularly rarefied, the resistance they faced would be far less than the models assumed. The jets would be able to travel further before slowing. They would have more room to stretch out before disrupting. This is plausible. The Discovery team has been studying the surroundings of Porphyrion carefully, and there is some evidence that the host galaxy sits in or near a particularly thin region of the cosmic web. A second possibility is that Porphyrion's central black hole has been producing jets for an extraordinarily long time. Most active black holes go through cycles. They feed for a few tens of millions of years, produce jets, then quiet down for a while, then feed again. If a black hole's active phase lasts only for a short time, its jets do not have time to extend very far before the engine shuts off and the plumes begin to dissipate. Porphyrion may be different. There is evidence in the radio data that its jets have been running with relative steadiness for hundreds of millions of years. The energy they carry has been delivered continuously in roughly the same direction for far longer than the typical cycle. The accumulated effect over that very long timescale is jets longer than any short-lived engine could produce. A third possibility involves the precise way that jets interact with their surroundings on intergalactic scales. The physics of relativistic plasma in extremely thin media is not fully understood. There are regimes, especially at the lowest densities, where the standard equations of fluid dynamics may not quite apply. It is possible that the jets are taking advantage of a kind of physics we have not fully modeled, traveling more efficiently through near vacuum than the simulations predicted. There may be other factors too. Magnetic field configurations, the detailed structure of the host galaxy, the interaction between the jets and the smaller galaxies they may have passed through on their way out. None of these alone is yet a complete answer. The picture is still being assembled. There is one more set of factors that researchers are taking seriously, related to the cosmic web itself. If Porphyrion's jets are traveling along a filament of the cosmic web rather than crossing through one, the physics of their propagation could be substantially different from the standard model. Filaments are denser than voids, but they are also more elongated, more directional. A jet traveling along a filament in roughly the same direction as the filament's long axis might encounter a more uniform medium than a jet traveling across one. The resistance the jet faces would change. The conditions for its survival over enormous distances would change. This is an area of active investigation. The orientation of Porphyrion's jets relative to the local structure of the cosmic web is one of the things the team is studying. If the jets are aligned with a filament, that alignment would help explain why they were able to grow so long without disrupting. The medium they pass through, while not empty, would be moving in a coordinated way that allows the jets to thread through it more smoothly than a randomly oriented jet could. There is also the question of feedback. As the jets deposit energy into the surrounding medium, they slightly heat and pressurize the gas they pass through. Over hundreds of millions of years, this feedback may carve channels in the medium, creating slightly thinner pathways through which the jets can continue to extend more easily. The jet, in this picture, is partly building its own road as it goes. The long jets of Porphyrion may have spent millions of years gently clearing the way for their own continued growth, allowing each new pulse of energy from the central black hole to travel a little further than the last. These are speculative ideas, still being modelled and tested. None of them is yet a confirmed explanation, but they give a sense of how the field is responding to the puzzle Porphyrion poses. The answer, when it eventually comes, will probably not be a single clean cause. It will be a combination. Environment, time, jet stability, medium pathways, magnetic field geometry, host galaxy properties, all of them contributing in different proportions to a structure that the old simulations would have called impossible. But here is what is already clear. The existence of Porphyrion forces a revision of how we model galactic jets. The old limits were wrong. The new limits are not yet clear. The field is, at the moment, doing the slow work of figuring out what the real ceiling is, if there is one at all. This is in its own way one of the more interesting moments in modern astronomy. A discovery that does not just add a data point, a discovery that breaks a previously assumed boundary and forces the theorists to go back and ask what the actual rules are. There is something humbling and something exciting about that. We thought we knew how big a galaxy could be. We were wrong. The universe is bigger than the models permitted, and the field, to its credit, has responded the way good science should. Not with denial, with curiosity. The new question is not, was Porphyrion measured incorrectly? The measurements have held up. The new question is, what are we missing in our understanding of galactic jets, and how do we fix it? We will not have a settled answer for years, maybe decades. The physics of jets at this scale is some of the most challenging in astrophysics. The simulations required are enormous. The observational constraints are still being gathered. The pieces will assemble slowly. In the meantime, the practical takeaway is simple. Porphyrion exists. Its size is real. The old theoretical wall that said something this large should not be possible has been quietly walked through. That is one of the small joys of working in cosmology. The walls keep moving. The universe keeps surprising us. Every time we think we have found a hard limit, we look more carefully, and the limit turns out to have been a soft one. It bends. It moves outward. It allows more than we expected. Let your shoulders drop. There is one more piece of the story to tell. You might imagine at this point in the story that we have arrived at the answer. The largest galaxy in the known universe. Porphyrion. 23 million light-years. 140 Milky Ways. End of search, end of script. But that is not quite where we are. In 2024, around the same time that Porphyrion was being announced, a different radio galaxy was being studied by other teams. Its designation is TXS0033 plus 2.52. The TXS comes from the Texas Survey of Radio Sources, an older catalogue. The numbers are coordinates. There is no mythological name yet. It is just a string of digits and letters in the catalogue. But the measurements being made of TXS 0033 plus 252 suggest that it is even larger than Porphyrion. The current best estimate puts its overall extent at approximately 26 million light-years, 8 megaparsecs, around 3 million light-years longer than Porphyrion. The data on TXS 0033 plus 252 is not yet as detailed as the data on Porphyrion. The size estimate is preliminary. There is ongoing work to refine it. There is debate, as there always is at the frontier, about whether the full reported extent should be counted as a single coherent jet structure, or whether some of the length comes from features that should be excluded. This is normal. This is how astronomy progresses. Big claims are refined. Numbers are revised, sometimes upward, sometimes downward. The current value is approximately 26 million light-years, and that value may change in either direction over the next few years. Even with all the caveats, the implication is unmistakable. Porphyrion is not, by all available evidence, the absolute final answer. There are other galaxies in the same datasets and in newer ones whose extents may be longer still. The record is still moving. This is one of the deepest patterns of the entire story. For most of the 20th century, the answer to which galaxy is the largest was IC 1101, The number was about 6 million light-years. In 2022, the answer became Alcyoneus. The number was about 16 million light-years, nearly 3 times larger. In 2024, the answer became Porphyrion. The number was about 20 million light-years, nearly 50% larger again. And already in newer measurements, a candidate at approximately 26 million light-years is being seriously considered, with more candidates likely still to come from the ongoing LOFAR surveys and from newer observations being made at higher sensitivities In roughly 2.5 years, the record for largest galaxy in the known universe has more than quadrupled. Not because galaxies are getting bigger, because we are getting better at seeing them. Each new technique reveals galaxies that were already there, but were hidden under noise or buried inside the resolution limits of older surveys. There is no obvious reason this trend will stop soon. The discovery team behind Alcyoneus and Porphyrion has been publishing additional papers describing populations of giant radio galaxies in the LOFAR data. Their statistics suggest that the very long ones are not freak occurrences. They are members of a wider distribution. The chance of finding a galaxy longer than Porphyrion somewhere in the sky is not 0. The chance of finding it within the next few years, with continued reprocessing of existing data and ongoing observation with current and next-generation radio telescopes, is reasonable. There is also a next generation of radio telescopes coming. The Square Kilometre Array, currently under construction in Australia and South Africa, will, when completed, provide sensitivity orders of magnitude beyond what LOFAR can currently achieve. It will be able to detect even fainter radio plumes than the current giants. It will almost certainly find more galaxies whose true extents have been hidden by the limits of older instruments. When the Square Kilometre Array begins full operations, the answer to which galaxy is the largest will probably change again, maybe several times. The record may extend into the 30s of millions of light-years, the 40s, perhaps higher. We do not know what the ceiling actually is, because the theoretical ceiling we used to believe in has already been demonstrated to be wrong. What we do know is that there is some kind of upper limit eventually. Galaxies cannot grow indefinitely. The age of the universe constrains them. The intergalactic medium, even at its thinnest, eventually slows any jet. There is a real number out there for the largest galaxy that physics permits. We have not yet found it. We may not find it for decades. But it exists. What this means for the question we started with is that there is no fixed answer. The largest galaxy is a moving target. Today it is Porphyrion. Tomorrow, by the time you watch this video on rerun in a few years, it may not be. The number on the textbook page will probably keep being updated. Every few years, a new candidate, a new mythological name from the giants of the old stories, a new record. In a sense, this is the most honest answer to the title of this video. The largest galaxy we have discovered is bigger than your imagination, but not because there is one specific galaxy that exceeds the human mind. It is because the very ceiling of the discoverable keeps rising. The galaxies that overflow the imagination keep arriving, every few years with new names and new numbers, and the imagination, by definition, cannot keep up. The imagination is one mind. The discovery is a moving frontier. This is what makes the modern era of cosmology so genuinely strange. We do not live in a time of settled answers. We live in a time of expanding answers. The universe is being measured more carefully than at any point in its history, and almost every time we measure more carefully, we find that it is bigger than we thought. Let your breath slow. There is one more thing to say. The last thing. Let us come back to the place we started. Tonight, we set out to find the largest galaxy in the known universe. The title promised something specific. One galaxy, one number, a clear answer. What we've found is not exactly that. We have found IC 1101, a yellow elliptical sitting at the center of a galaxy cluster more than 1 billion light-years from Earth, holding the record for the largest stellar extent we have measured. Roughly 6 million light-years across, roughly 100 trillion stars. The largest cathedral of stars we know. We have found Alcyoneus, a radio galaxy in the constellation Lynx 3 billion light-years away, whose plumes of plasma reach across 16 million light-years of space. held together by the patient work of a supermassive black hole running for hundreds of millions of years. We have found Porphyrion, a radio galaxy, in the constellation Draco 7.5 billion light-years away, whose plumes reach across 23 million light-years on the scale of the cosmic web itself, with light still on the way. The image we see older than half the universe, and we have learned that even Porphyrion may already be overtaken by candidates whose measurements are still being refined, whose names have not yet been chosen, whose places in the moving record will be assigned in the coming years. There is not one largest galaxy. There are several depending on how you measure, and the rankings keep shifting as the methods improve. That is the quiet thing this script has been moving toward the entire time. The word largest, when applied to galaxies, is not a property of any single object. It is a property of the question being asked. Stellar extent gives one answer. Halo extent gives another. Radio extent gives a third. And inside each of those categories, the leaders keep changing every few years as old data is reprocessed and new data arrives. If you took the word largest and tried to nail it to a specific galaxy, the galaxy would slip out from under it. The label refuses to stay attached. It moves with the ruler. There is something beautiful in this. Cosmology is one of the rare fields where the ground keeps shifting in a satisfying way. The shifts are not random. They are improvements. Every revision makes the picture more accurate. Every new ruler reveals a layer of the universe that older rulers could not see. The ground moves, but it moves outward. The universe gets larger in our understanding, not because it is growing, but because we are seeing it better. For most of human history, the answer to almost every question about the night sky has, eventually, gotten larger. The stars were once thought to be lamps hung on a celestial sphere. They turned out to be distant suns. The Milky Way was once thought to be a band of glowing gas. It turned out to be a galaxy. The galaxies were once thought to be nebulae inside a single universal system. They turned out to be separate islands. The universe was once thought to be a few thousand light-years across. It turned out to be billions. Every revision in the long history of astronomy has made the universe larger, never smaller. The shrinking direction is not available. There is no way for the next discovery to make things smaller than we thought. The arrow only points outward. The largest galaxy is the latest chapter in that long arrow, the same arrow that ran through Herschel's catalogues, through Hubble's photographs, through the long, quiet work of generations of astronomers, who looked at smudges and patches and clouds and slowly figured out what they were. The arrow keeps moving. It has not slowed. It will not slow in our lifetime. You are alive at a particular moment in the arrow. A moment when, every few years, the largest known galaxy gets larger. A moment when ordinary research papers come out, in modest journals with measurements that, a generation ago, would have been considered impossible. A moment when the line between the imaginable and the real keeps being redrawn. That is the meaning of the title. The largest galaxy we have discovered is bigger than your imagination, not because of any single galaxy, because the meaning of largest itself has expanded in the last few years in ways that no human mind could have predicted in advance. The frontier is in motion. The number is provisional. The next galaxy is already there, waiting in old data for someone to look at it carefully. There is one more thing worth saying about why this matters. Before we end, if you live a long human life, you will see this frontier move many times. The records being set now are not going to hold for long. Within a decade, possibly within a year of this script being written, somebody will publish a new measurement of an even longer galaxy. The numbers will keep climbing. The names from old mythologies will keep being assigned to new giants. The textbooks will keep needing updates. This is one of the small gifts of living in this particular era. There have been other eras of astronomy when the field was relatively settled, when the major questions had agreed upon answers, when the textbooks could be printed and trusted for decades. We are not in such an era. We are in one of the open phases when major numbers are still being revised, when entire categories of objects are still being discovered, when the imagination of what is possible keeps expanding faster than any individual mind can keep up. For most of human history, the largest galaxy was unknown because the concept of a galaxy was unknown. For most of the 20th century, the largest galaxy was thought to be a specific elliptical at the center of a specific cluster, and the answer was stable enough to be taught with confidence. We are now living through a moment when that answer has come unmoored. The record is in motion. The next chapter is being written, somewhere in the data of telescopes that have not yet finished their surveys. Most of the discoveries in this script have happened in the last 3 or 4 years. None of them existed in the textbooks of a decade ago. Several of them have already been overtaken by even newer findings since the time of writing. That is the speed of the frontier right now. It is a quietly exciting time, not in the loud sense, not in the way that captures headlines and trends online. In the slow, patient sense, the way that mattered to Herschel in 1790, and to Hubble in the 1920s, and to the LOFAR team in 2024. The sky has more in it than we have yet seen. The instruments are improving. The methods are improving. The frontier is moving outward slowly and steadily every year. If you are listening to this with the lights low, in the quiet hours of the evening, take a small comfort from that. The universe is not finished revealing itself. The largest galaxy we know about is not the largest one that exists. Somewhere in the data being collected right now, in observatories you have never heard of, in fiber optic cables in the Netherlands and in Australia and in South Africa, new measurements are arriving. The next giant is already on its way to being noticed. You do not have to wait up for it. The discovery will happen whether or not you are awake, but is happening now, even tonight, in places where the work continues at the pace of careful, patient science. The universe keeps offering itself to be measured, more carefully each time. The frontier keeps moving outward. You have a small body. You are lying somewhere, perhaps in bed, perhaps near a window, perhaps with the lights low. The room around you is bounded. The ceiling has an edge. The walls have corners. Everything in your immediate surroundings has a size you can hold in your mind. Outside your room is a planet. The planet is bigger than your mind can really hold, but you have seen pictures and you know it is round and you know roughly how far across it is. You can almost hold it. Outside your planet is a solar system. The solar system you can almost hold too with effort. Sun in the middle. 8 planets. Dwarf planets at the edges. Familiar names. Familiar order. Outside your solar system is your galaxy, the Milky Way. 100,000 light years across, 400 billion stars. You cannot really hold this. It is too big. But you have seen the pictures and you accept it. Outside your galaxy is everything else. Tens of billions of other galaxies. Some smaller, most about the same. A few much larger. And among those, somewhere, the ones we have been talking about tonight. The giants in the data. The plumes extending across millions of light years. The supermassive black holes patiently running their engines for hundreds of millions of years. Porphyrion. Alcyoneus, IC 1101, names from old stories given to objects we are only just beginning to see properly. They are out there right now. The light from them is still arriving. Some of it is reaching the surface of your planet at this very moment, as you breathe slowly, as your eyes drift closed, as the day ends and the night settles in around you. You do not have to hold any of it. The galaxies will go on existing whether or not your imagination keeps up. The frontier will keep moving whether or not anyone is awake to read the next paper. The universe does not require you to picture it correctly. It only allows you to live inside one quiet corner of it on a small world that turns once a day, under a sky that hides the largest structures we know. For tonight, that is enough. Tomorrow, or whenever you wake, the record may have already moved further out. The largest galaxy may have a new name. The number may have grown. For now, let your shoulders drop. Let the room around you be the right size for your body. Let the universe be the right size for itself. They do not have to match. They never have. The galaxies will still be there in the morning, in the same places, in the same patient.